So first, I will provide a brief overview of deep learning concepts and how deep learning is related to notions such as invariance. Actually, the whole grail of deep learning is to capture invariance indeed. I will then delve into how group theory can be effectively utilized to model invariance for computer vision tasks, moving beyond classical static data augmentation schemes. I would like to talk about how it is difficult to apply a proper data augmentation scheme to dynamical system or some dynamical data, such as time series. Lastly, I will discuss some theoretical results for augmenting time series data, supported by some compelling experimental results that showcase the practical effectiveness of our technique in real-world applications. So the general theme here is that when we think about deep learning, its success depends mainly on two things, right? So having the data and a lot of computational power. But often it is not feasible that to collect or have millions and millions of data with their labels and in different target domains. So oftentimes we have to exploit some additional information like the structure in the data itself, such as invariance actually, to help to narrow down and help our models to learn and to focus on what is actually important in the learning task. So this takes many different forms, and sometimes we kind of bake those invariances in the way that how we design the architecture of the ML or of this machine learning model. So like the group convolution neural network or some equivariant networks and so on, sometimes this invariance shows up in transfer learning. I want to transfer the same properties from different two or multiple domains. Sometimes it is in the data themselves, how to represent the data. And how do we represent the data to be invariant to perturbations or transformations? So that is what we call data augmentation, actually. And it has been used a lot in empirical studies to help the learning task to encode invariance. So this slide, for instance, illustrates the concept that convolutional neural networks, CNNs, do not inherently capture this kind of rotational invariance. Here, two images of the same cat are shown. One is a normal upright position, and the other one is rotated. These images are used to demonstrate how the orientation of input images affects the output of the CNN. Basically, to sum up here, the slide shows the limitation of standard classical CNN architectures in handling those flipped images, and hence the need for techniques that can introduce those flipped invariances into these models. So to avoid our model to over-index on the orientation, we perform data augmentation. So we generally apply these kind of transformations here, like flipping, rotating, or even somehow like cropping these images so that in the end, you are still having data sets of cats, but your neural network might be less likely to learn that the orientation is what is important for our downstream task. Here's another example of data augmentation using some real-world kind of medical data, same example. Here we can see like another example of the performance benefits for using data augmentation. These experiments show that the test accuracy or the error is better when we use these data augmentations in a more empirical way. So the top one is with the data augmentation, and the blue curve is without data augmentation. So we have less accuracy. So now, given all of that, we found that the literature hasn't quite addressed explaining exactly in more mathematical terms why data augmentation works, and more importantly, when it should work, although a number of recent works are kind of like starting touching upon this area. I guess what is missing is how we can precisely explain the performance benefits that we are seeing from a theoretical point of view, and how do we model the data augmentation process, generally speaking, and how do we actually prove by how much it should improve our learning task performance. So basically, there is no mathematical ground truths of why this is working and why not, and when it should work, when it should not work. So it's just, so far, it has been like highly empirical. So the current stage of the literature is that a lot of work are doing that augmentation in a hand-picked way, and most of them are domain specific, and hopefully at the end I will show you how we can quantify this mathematically speaking, and how we can also design new ways to do data augmentation. So before any attempt to model the problem, the first thing to do is to assume our data is drawn from one distribution, let's say x1, x2, xn, like images, let's say. Then we consider a group of transformations which can act on the data space, which is a manifold. Now that we have a group structure, let's say some rotations, we can define transformations, flipping, rotations, or shifting. We can, so we call this like the group of rotations, for instance, if you use some rotation operator. Now, one way to characterize that augmentation, again, in computer vision sense so far, is to assume that these transformations maintain some notion of approximate invariance for the data distribution, right? So X is the cat image, and G dot X is cat with some angle of rotation. Here, for instance, 45 degrees. In case when it is exactly the same, or we have exact invariance, we say that the original distribution of the data and the transformed one are exactly equal in some distributional sense. And where a cat is still a cat, we have the same object, right? But however, in practice, things are never exactly the same. So in order to characterize what we mean by approximately invariant, we need some sort of measure, a metric, in these data manifolds of images. Like here, what I call like the Wasserstein distance or metric. Is it how we can compute how far my image flipped is far from the original image? It's a kind of a measure. So now approximately invariant simply means that the distance between the probability distributions before and after the group action is small. So we have an image, I flip it, is it far or not, okay? So that's how we capture some sort of measure before and after transformation. But it is not clear what does data augmentation mean for time series now. Now I'm moving from images to dynamical data, okay? So for instance, can you tell me if these two time series here in C are the same? And if it's the same, in which sense they are the same? Are they invariant? What does invariance mean actually for time series? Can the topology or the shape of the time series be invariant? Can we actually measure that? So all of these are open questions, and it's not like images where the cat is just a cat. Let's say here a second example, the E picture. If this is a time series after applying a rotation, like what is commonly done in image recognition, cat flipped cat, but now we have a time series. If I flip it, it is the same time series, maybe not. It's going to be the same cat, but maybe not the same signal, right? So it's not quite intuitive. So a general framework for fundamentally understanding why data augmentation works has not been addressed in the literature. These are the fundamental questions I'm trying to share with you today. Okay? Any questions so far? No? Good. So the situation becomes even worse in certain critical applications. For instance, in finance, we have only one sample at hand. Like let's say, at ETF S&P 500, I have only one signal. So what should we do with this? How can we learn from only one sample? Okay. So time series prediction problems highly depend on the observed historical time series data during the training. More specifically, we train our ML model using only one fixed kind of historical time series, which can lead to overfitting. However, the fixed historical time series is only one particular realization of an unknown stochastic dynamical system, which I don't know. If I know the model that can generate the time series, I can just use it. But usually no one knows what's the dynamics of the S&P, right? So that's a bit the bottleneck here. So the question is, can we train using more realizations, even if we don't know the underlying dynamical systems? And the answer could be yes, sometimes. And one way is to use data augmentation. And we conjecture in our work that training with more kind of realizations, more than one signal, can lead to better learning under some conditions. Okay, so we have S&P. Can we have many like S&Ps, and can you have a better performance? So that's the whole grail now. Okay, but how to get something like S&P? That's the question. So kind of before starting to show you how we can do this, let's kind of define the problem mathematically speaking. Given a loss function, how is data augmented? How this procedure is done in practice of data augmentation? So to start with, here is a standard classical ML loss function, like just mean of loss. I want to minimize some loss, right? L could be the mean square error, for instance, or cross entropy, or any measure. And obviously, we would like to minimize this loss. This is like a standard procedure for any ML model. In practice, for data augmentation, we apply some random augmentation or random transformations, f of x, f sub t here because I have the time component, as I mentioned, for time series. And then we apply basically stochastic gradient descent to minimize this loss function. So far, so good. This is well known, and so nothing is new here. So this data augmentation process now can be viewed as not minimizing the original loss function that I showed in the first equation, but actually minimizing this augmented risk, under which we take this expectation over the augmented sample space. Now we have the loss of f of x, and we have to take an average because I'm picking randomly those transformations from a set of transformations, obviously. So one comment here is we have this theta in these equations, which connects us somehow to a concept called the maximum likelihood estimator, something like how good my parameters are. And later I will show you why data augmentation leads to better MLE or better parameters, okay? Because we minimize over the parameters of my neural networks if it's a simple neural networks. So that's the problem statement. That's how we train the model so far. The first in the top is without augmentation. The second one is with augmentation. Now I'll start talking about the paper that has been published last year in iClear. So I will start with some mathematical background, and then I will move to applications. So I will go slow here a little bit, okay? So I can explain better what I mean by these equations. So basically, what we are looking at here is the standard arguments for something called the kind of regret bounds. So what is a regret bound, first of all? Well, a regret bound measures the performance of an algorithm. It's something I use to say if this algorithm is good or not good. That's it for now, okay? To give you some intuition, what this regret bound means. If we want to estimate a parameters in a stochastic environment, we often give its mean value and its kind of standard deviation, right? I have some kind of uncertainty. I will give you a value plus STD. That's for a one scalar or one parameters. I like to think about regret bounds as a generalization of confidence intervals when estimating the performance of an algorithm or a model instead of a single parameter. So we have a parameter, we have its confidence. Now I have a model and I have its kind of confidence, how good I am and how certain I am. So that's kind of the same philosophy here in a higher level again, okay? That is a regret bound for my model. Good. So then here we have a term in the left with the green is what we call the generalization error, or sometimes simply the risk in machine learning. And the term in the right is called the regret excess risk. And equation one is called the Rademacher complexity bound. It simply tells us how good is our parameter estimation compared to the optimal parameters. That's it. I have theta hat is my estimation, is what I'm learning. Theta star is my supposed kind of true optimal parameters. This difference is kind of the risk, and it's bounded. We have an error, okay? So that is well known. This first inequality is easy. I can derive it step by step in 15 minutes. It's not complicated at all. Just telling you how good you are as compared to some sort of optimal parameters. That's a well-known. And the bound depends on the first term called Rademacher, which is like R sub n, and a second term that depends on the number of samples, let's say, like n. If we have a high number of samples, n goes up, and this square root of something over n goes to 0, right? So we have a more tight bound. So that's why deep learning works in general with a lot of data. So big data means n goes to infinity, where it's a big number, ratio is small, we have a smaller bound, which means less risk, basically, okay? Now, that's the first equation is well known, okay? So in this work, we show that if we want to do the same philosophy, the same derivation, the same mathematical tools, we have 3 or 4 inequalities. If you have them, we can just use them and deploy them to derive these equations. But in the context of data augmentations, we got one extra term. We have the same bounds again, the same R and the square root stuff. Extra term, oops, here, using like D. D is called like the divergence. How far my augmentation or my transformation f of x is far from x. How far my new time series is far from the original time series. It's something that is just like showing up and popping off in the inequality bounds. And from 1 and 2, now we have 2 equations, one bound with no augmentation and a second bound with augmentation, with one additional term. So from 1 and 2, and some technical kind of inequalities, we can derive 3. And what we can see is that the augmented or Rademacher complexity bound is governed by these 2 additional terms, delta here, this term here, and delta is a negative term as shown in the expression below here. It's kind of negative. And the second term is capital D. Again, it's the divergence between our original data distribution and the augmented one. Divergence is like a distance, but it's not a distance, something like that, okay? It's like a distance between 2 distributions, let's say. Now, as a special case, if this distribution are exactly invariant, which means f of x is similar to x, then this distance goes to 0, right? And if it goes to 0, Then Rademacher n with augmentation is less than Rademacher with no augmentation plus delta, and delta is negative, so the bound is tight. We have a better Rademacher with the augmentation scheme. So now decreasing Rademacher simply means ending up getting a tighter bound for the risk, which is synonym of better learning. That's the whole storyline here. If we are able to design like a machine learning algorithm such that this divergence x f of x is very, very small, then it's game over. You have a better learning. If you have an algorithm such that you are doing transformation on that augmentation, but your transformations, f of x and x are not closed in the sense of divergence, then most likely your data augmentation scheme won't give you a good results because it will be a loose bound, okay? So that's the storyline behind this here. So now the question becomes, can we impose such a structure in the input data so that my divergence term goes to 0? So that's the whole grail now. Now the question is find a way such that f of x and x will be very close. Okay, so that's the slide is about this. So can we move on? Good. So some recent work presents different invariant distances for time series. For instance, people said that there is no universal distance actually that is perfectly invariant. And the choice of the distance depends on the context and the task to achieve. So it's still kind of hand-wavy approaches. So there is nothing perfectly available for us. So here is one illustration of our technique that we use in that paper. So we developed some sort of procedure to overcome the partial observability and the non-stationarity of the input training data sets. So we start here with a time series on the left, the orange one, and we use a formula to compute new values, x tilde, the blue ones. And this example sets lambda to 0.8 or 0.8, but in practice, lambda is sampled from a distribution. I can just sample any value from, like say, I have a kind of uniform distribution. I can just sample many lambdas, and for each lambda, I would have a new blue signal, okay? So we generate many of these interpolated time series. Now, the important thing is that this difference between the generated time series, the blue ones, and the original one, the orange ones, is bounded. So this D of orange comma blue, orange is x and the blue is f of x, this distance or divergence is bounded. So that's what I call dx f of x in the bottom equation. And the bound here depends on a very nice things, like the characteristics of the time series, like the maximum value of a time series and the number of time steps for my time series. So these are something I can easily compute and put them in the bound. And if the bound is big, my distance dx f of x is not good. But if I have the maximum height and the length such that we can compute these distances, and if the distance is small, then that's a good sample for my data augmentation. I can take this sample. So it's kind of, we have control on how to control my sample of the data sets using a bound that depends on my data. So this gives us a notion to control our divergence and keep it small, which leads us to define a notion of invariance or approximate invariance from time series. So hence, I'm starting now to build some invariance notion of time series. Okay, so we want now to understand more precisely what actually happens during learning in the parameter space. So I start by taking some difference between the mean squared error of my estimator and the mean squared error with the true parameters. And here again, we see this trade-off that I'm talking about. So basically, so I can say that this difference between the mean squared error of augmented minus the vanilla one, which is no augmentation, is negative. Because of this variance reduction term, the kind of green one is negative, but we do also have this additional term called the bias in the red. And the bias, again, depends on this distance or divergence, capital D, between the original one and augmented one. So if it's small, delta goes to 0, and this kind of green term is negative. So I will end up having a better MSE. MSE, again, it means squared error of my augmentations. Theta aug is less than MSE of theta. So I'm sure under such conditions or some circumstances or hypotheses or assumptions that this new MSE with augmentations is better. That's how I can guarantee that augmentation can lead to better performance. And this is the last mathematical slide, okay? I promise. So the theoretical results I have shown in the couple of slides so far show us what we call finite sample analysis. Finite sample means I have a finite number of data points. I have, like, say, 1,000, 10,000 samples, okay? But here, so this theorem simply says that using some technicalities, the same logic holds in the asymptotic regime when we assume we have a very, very large number of samples, like when n, and n is the number of data, goes to infinity, what's going on? So basically, so what happens to my learning algorithm? Is it going to be good or bad algorithm? Okay, guys? So here the main takeaway, if I can summarize this slide, is, or the main message to keep in mind, is that our augmentation technique also reduces the variance in the limit, where the number of samples becomes very large. Variance means how certain I am. I mean, I have a path, but I have a small variance, and I'm sure that that's very good, okay? So we can have this property in the limit and show we have less variance. It's just a consequence of a law of large numbers, basically, okay? So that ends the mathematical components. Now let's move to real-world applications. So in this work, we use 2 synthetic data sets and 4 real-world data sets. And in all cases, the learning performance with our augmentation techniques outperforms the one without augmentation. So here, I'm showing results from 2 finance tasks. The first one is stock prediction using some regression, and also in portfolio management using like a kind of reinforcement learning approach. For all of these charts, the augmented results are in the blue, and the non-augmented one are in the orange. Now let's focus on the first one. For the stock prediction example, we showed the learning performance using 3 indicators: the proportion of the correct predictions, the upper left figure, where the higher the better. So the blue is higher, so it's better, because it's a proportion of good kind of predictions. The compound annual growth rate is in the middle. And here again, the higher the better. So the blue is higher, so it's better. And the MSE, the mean square error again, is in the upper right corner, where now the lower the better. So a lower MSE, the better. And as you can see, even the variance, this kind of shaded area, the blue is less than the orange one, which is bigger. So we have high variance if you don't use augmentation, okay? So that's one case study using regression for stock forecasting. The second one is portfolio management using kind of reinforcement learning model. And the performance here again, gap between the augmented one and the non-augmented one increases with the training steps as shown in the bottom left. But here for RL, the higher the better, because I'm maximizing my reward function. So it's a maximum stuff. So here in this setting, we have 2 sets of, I would say, ODEs. And ODEs here can be thought as a generator of time series. I mean, the solution of these ODEs are 2 signals, which are and our task here is to classify these 2 signals. I have the blue and the red, and it's hard to classify by eye. It's a bit kind of tricky. but the AI can do it actually. So ODE with different parameters invoke different dynamical behavior of time series solutions. And in the left plot, for each class, we generate multiple solutions using the corresponding ODE with different initial values. And to make the learning task a bit harder and difficult, we add random noise on the solutions. And the right plot shows that our test performance curves using the original non-augmented time series data, the red one, the time GAN, which is kind of some sort of state of the art for data augmentation techniques for time series using machine learning, is the green one. And our method, the blue color called RIM. And as you can see, our method outperforms both the other two techniques. So the blue has higher accuracy compared to the green and the red, following the same kind of mathematical procedures. That's one case where here the accuracy is how good I can classify the blue and the red signals. It's a classification problem. The first one was more for a regression forecasting problem. Here is the same philosophy. This is like a second example similar to the previous one, where we consider some kind of trigonometric ODE solutions instead of the exponential ones. The same logic. Here, time GAN results are worse than the non-augmented case. So here, the green one is the worst case. And our technique outperforms both methods again. So we have a better accuracy when we have to classify those signals, 1 and 2. Now, like another example, which is like a binary classification task, is associated with predicting the patterns of user movements in a real-world office environments from time series that we kind of capture from a wireless sensor network. The left plot shows data that have been collected during movement of the users and labeled to indicate whether the user will lead to moving to a new room or not. I'm moving, I will stay within the room, or I will go out from the room. So that's the kind of the data, and we have sensors, and we have 2 signals, and we have to classify whether the user is leaving or not the room. So in the experiment, we use a subset of the data to form a small training data sets just to challenge our classifier. And in the right plots show that we achieved better and more robust test accuracy compared to time GAN and to non-augmented one as well. So it's kind of like a new case study also showing that we can do better. What else? Here in this example, the data set contains time series corresponding to measurement of engine noise captured by a motor sensor. So we have a car, and I want to know whether I should do maintenance or not. It's a very highly critical kind of application. And the goal is to detect, again, the presence of a specific issue within the engine by classifying whether each time series has a symptom or no, okay? As you can see in the left, it is very hard to classify signals by only using your eyes, just like it's almost impossible for us. We sampled here 100 time series from the data set to form a small training set, again, to challenge our classifier, because small is hard. If you have a lot of data, it's easier, right? And also we use the same number, so 100 time series for the testing as well. As shown in the right figure, our method outperformed the time GAN and the non-augmented case on the test accuracy again. So that's it for today, and thanks very much for your talk. هذا مقلب وهذا رجال بغيتو أنا موجود باش نجاوب أسئلة. Yeah.
Question regarding the marker down.
Yeah.
It depends on the lecture constant of the model. For more deep learning, or that constant.
So for this red matter bound, it depends on the lecture constant of the model, the loss, which depends on the model.
Yeah.
So this question, did you try to make the data augmentation model specific to and a constant that lecture constant?
We did not. No. Nope. But usually it's an assumption used in many machine learning models. And we hope that after stacking layers, we keep some sort of contraction mapping between layers, but we can detect it somehow. If it's not gonna be the same, then this approach won't be, I mean, we can't prove it mathematically. So the Lipschitz assumption is our assumption to prove these bounds. If it's not Lipschitz, then this is not gonna hold anymore. And hence there is no guarantee.
Yeah, so basically my question is, if you can estimate that Lipschitz constant, then you could probably, for that model, know what a good data limitation looks like.
That's a good comment, and we did not did that, but I think it's good to keep exploring this avenue.
Thanks for this.
Nice. Thank you very much for your question. But by the way, Sufyan, do you know how we can some sort of leveraging these kind of properties of these Lipschitz functions from the data? It's hard.
Usually for deep networks, Lipschitz constant
Loads exponentially
With depth. So basically, okay, that's a good point, guys. So in this kind of architecture, we have a shallow networks. It's not deep learning. We have just a few neurons and few layers because we are kind of mainly targeting use cases where we don't have a lot of data. We have only a few data sets. And from few data, I want to learn how to classify, how to control, how to forecast, which is very challenging to do if you have a small data set. So the models themselves are very, very small and shallow, so which maybe makes sense why it's working.
So thank you for the presentation. So I've seen that the data organization from here and study. My question is about what about the other type of data like text or audio? What is this?
Sure. Thanks for the question. I'm starting to kind of explore this kind of area of LLM and how to augment. For instance, yesterday I saw some group working on kind of translation stuff. And let's say one way to augment would be to use the text and translate first, but then do some paraphrasing of the same, and then retranslate. And hence we can, with some paraphrasing scheme, we can augment the signal and it's close to the original one and stuff like that. What else? Text also depends on many things, like maybe you can crop a little bit the first and the end, but you're gonna lose some context. I think it's not clear how to do it in practice, but it's a very good question. But one way is to use some paraphrasing stuff. Any questions? Of course.
Did you try to make any money with it? Trade this up.
I pitched this last week to a hedge fund in New York. نبقاش لي كيسيون صافي هاي سولو ماشي مشكل. واحد بغا يسول عطيه.
My question is, this data acquisition technique that we can apply to science theory, just adding the components of control, and like you talked about reinforcement.
Right.
I think it can transfer, so you can give insights on like transfer and this kind of things to control and use things to control them.
Sure. Yeah, easy. In control, specifically in the reinforcement learning, we have environment, we have the agent, and they play or they interact. So in this case, I showed, let me go back. Yeah, this one. So it's a portfolio. So we have the state or the environment is say the stock price, feature of the stock, open, close, high, whatever, you know, the volume also. And these are the state. The state is like a kind of tensor where I'm stacking the price, the volume, and also some kind of historical data. And it's a huge tensor, and this is one state. But now, if I use this same scheme of augmentation, I'm just augmenting each single input in this tensor using the same logic I did for at one point, but here we have a tensor, and we just augment the state space of the RL. And by just augmenting the state space in the RL, it will impact the policy. The policy converges to a better policy. That's by playing with the state information.
So the data composition would still be close to the distribution that we already have. So maybe we should have some conservatism like offline.
Well, so I think this is a big trade-off here. I mean, so you would like to have some diversity to learn, but also you have to be close, because the thing is, images are static distributions. That's okay. And if I flip this, it's still the same object. If I flip a time series, it's not the same object. So we need to be conservative somehow. Otherwise, you are not learning what you should learn. So we have to be careful. So we have to relax this kind of invariance more than images, but you have to control it. That's what we define bit bound with some, which depends on time series properties. So it's something that you have to control, I think. So that's.
That is a discount link, so we have some changing of this. That if we see them as the predictions of view predictors, sort of asserting or distance to the distribution.
Some sort like this. It could be. It could be because we know that the price itself is just a noisy it's kind of I mean, it's called like a partial observable signal. It's only partial observable. It's not the signal. Okay, so it's by default something noisy. Indeed. Good question. You first.
All right. So thanks. Personally, I've never worked with time series before, but just like 2 days ago, maybe a week or so, Google released a foundation model, I believe, time something. It's relatively small. So my question is, like, is there any efforts, or have you even tried yourself, like, to try to somehow generate synthetic data agents model? Maybe like, I don't know how it works honestly, but the idea for me here is just to use the model itself in order to generate synthetic data out of the same distribution of some input data, just for the sake of augmenting the data set, the corpus itself. So is it something?
What's the name of the model you said?
Times XM, I'm saying, or something. It's a decoder only, a Bayesian transformer.
Bayesian
I
transformer.
believe 200 million parameters.
No, I'm now moving to like extension of this kind of work, using transformers and something called state space models as well. Basically, in this work I'm working on is, instead of focusing on the signal itself, we decompose the signal into modes, and these are called like dynamic mode decompositions. It's like Fourier modes, but with some dynamics, let's say, make it simple. And instead of trying to learn the time series themselves, we learn how to regenerate the modes with a transformer. And then once we get them, we can just reconstruct the signal and get a new time series. So that's what I'm currently working on, and maybe I should take a look into this paper you just mentioned. I'm not aware of.
I don't know if they're released yet.
Oh, okay, it's
The model is released. The model is there, so I guess
it's a model.
If it's not there, it will be so. But the idea of generating signals, like talking signal and like try to continue with this model. Because I have no idea. And see, I'm just exploring it. It's itself, or it could be happen. I don't know.
Yeah, I mean, I'm not aware of this, but if you give me the name, I can take a look into it. But thanks for bringing this.
Okay, thank you.
We have a question. Aisha.
Thanks for the presentation, was very interesting. I only have one question about one use case that you were talking about was the one that checking whether the person inside the room or outside. So here in this data set, you were taking like the signal, like, I don't know, maybe,
It's called RSS. I have no idea what's this. I'm not taking the data. It's called the radio signal strength.
oh, okay, yeah, so, no, we don't. But the thing is that here you only do the situation if the person is inside the room or outside the room.
Living room, walking living room.
Okay, so there was.
Feature pattern. If someone will or want to leave the room, we have a special pattern. And if someone wants to stay in the room, we have a specific signature.
Yeah, yeah. So here it's only like for two cases, leaving the room or being inside the room. So you didn't try with data set where you have like much more, like for example, taking stairs or also like, I don't know, moving from indoors or outdoors.
Yeah.
To see like if you want to data work with have or not.
Yeah, and I think the approach, I mean, being a binary classification or kind of multi-class classification should work in principle. It just, I don't have the data for it. I just use the UC Berkeley time series kind of repository, which is well known, and this is one of the data sets over there. So maybe, yeah, if I have something I didn't build myself, I'm just using so many data benchmarks data sets from a well-known website. So this website is, if you want to publish in time series, usually people go and use these benchmarks, and this is one of them. So if I can get this data, I would love to test it.
Yeah, like, we also like for us, we get our own data and it's really a problem to like, yeah, so it's a problem to like have data that you can rely on.
I see.
For example, labeling and stuff, you never know if the person made an error or something, so that's why you do it yourself.
Sure.
And I was like considering like thinking like doing also disciplinary more data instead of like going and doing the and you need volunteers, you need a lot of things. But I'm not sure if this also would be working or not. That's why
So,
I'm having this question.
Give me the data, and then I will test it for you.
Okay, I can do that.
Okay.
Thank you.
Thanks.
I guess this will be the last question. Bonjour, j'aimerais vous remercier d'abord pour votre présentation qui nous a montré l'investissement. Ma question, j'aimerais bien savoir, avez-vous exploré d'autres techniques de modélisation de données au-delà des données synthétiques?
هنايا راه عندي جوج سينثيتيك باقي كلشي ريال وورلد داتا. Finance is real world, real stock market stuff. This kind of the indoor user movement is real data. The fourth engine is real data. So this is real data, this is real data, this is synthetic data. This one is, and these two are real data. So 4 out of 6 are real data sets and only 2 are synthetic. Make sense?
Thank you.
Good.
Thank you very much, everyone. I hope you stand in so next step here, ceremony award. On was hard use Koshbinas for Spartan for campaign.
ladies and gentlemen دونك صافي لقى صافي سالينا شكرا بزاف على الصبر ديالكم. Thank you so much for the effort you made صراحه في the last couple of days. You've, as I said, you've overachieved صراحه. You over-delivered. I'm very proud of you all. What? Sorry. Oh, okay. We can wait like for 3 minutes. There's a video being shot right now, an interview. So, نسكتوا واحد شوية. Were absolutely amazing صراحة. I'm very proud to be part of this community, a part of these people صراحة اللي جايين I think from all across Morocco just to develop and be the new generation inshallah in either IT or en général in software en général. But that's me again. But yeah, before we start, we need to thank some specific people, to be honest. First of all, 1337 Sol provided us with the talents and the logistics in order to achieve what we achieved today, or these last couple of days. Again, you can thank the rest.
Je voulais juste revenir sur Mathé Maroc au 1337 AI, le club de l'intelligence artificielle à 1337. Ces deux associations sans qui l'événement n'aurait pas eu place. Ensuite, il y a notre partenaire officiel, Adria Business and Technology, sans qui aussi l'événement est Ikoun. Et ensuite, Cultural Communication Hacking Paste for all technical support and on au cours de tous les années. Merci beaucoup, Ikoun Camille. Ensuite, au cours de l'événement, qui nous a engagé le Shinjar, qui est des mentors, qui est des organisateurs, des jurys, des déplacements, des experts, et le Shinjar, عاملين نحققوا la deuxième édition de ThinkAI. شكرا لكم كاملين.
Donc, قبل ما ندوزوا لتوزيع الجوائز, I would just like to say, if you win or you don't win, it doesn't matter. What matters is you all are winners in my eye, at least in my eye. in their eyes as well. So it's our eyes. But yeah, without any further ado, we're gonna start with the third position. And to announce it, we will welcome both Madame Lubna Badour and Mr. Sufyan Hayy. تقدموا مشكورين. Thank you so much. Do you know the name of the winners or not? Okay, perfect. I want you to say 3, 2, 1, and say the name. Okay? Just give it to the response. Just where you are. You can scream it together. There you go.
You ready?
You click just once, huh? 3, 2, 1. Sorry. This. Wait. عبد الجليل. There you go. سميتي وليد. خذ بالك الأولى. شوف. سير. خش في الداخل. Yunus. There you go. And Ayub. There you go. هذه خلص. صورة مع الشكتاو. عطاو الفلوس صافي نساو الفلوس. Thank you so much, Madam Lubna. You wanna say what? You want to? أنا كنت أعطيت زعما الحقيقي. If you want to, you don't. It doesn't matter. You can. Yes. You can.
Okay.
You took the 3 can. Oh no, Shalus. There you go.
Hello, everyone.
If you do you want to have a talk? You can start. ماشي هضر مع الزينون صافي.
And I would like to talk about Andrea, and an official partner of the Network Association. And first of all, thank you to all the participants for their engagement at this event, organizers and coordinators, and everyone who helped make this event success. Also, I would like to say that in the name of the whole team of Andrea's team, I would like to say that we're very glad to collaborate with Mathematical Association, especially because AI Hub. It's a really passion that we share with Mathematical and all the children and etc. Donc, on est très heureux de collaborer avec eux pour les événements et de voir les jeunes qui créent des solutions si innovantes et créatives. Donc, excusez-moi, un terme français et anglais. Donc, bravo à toutes les équipes, même si et voilà, merci.
Alors, j'aimerais vous dire franchement, je suis vraiment surpris de le niveau de la hackathon. Je suis très bien chiqué qui est vrai. Moi, je veux dire, حاجة مهمة هو إنه دابا خدمتوا على les idées. Les idées, c'est quoi les idées? Il faut encore développer هادشي. نبغي نشوف مثلا quelques idées من هادشي يكونوا des startups. الخدمة هي كلشي. Bonne chance et voilà, continuez.
Thank you. Again, بعجالة ندوزو our second position, second spot. and it will be presented by none other than Madame Hasna. Hasna Bel what? Hasna Bel? Wow. And Mrs. Aisha, what is it? Miss Aisha. Thank you. We go again, that's the concept. When you're ready. Ladies first, راكم بجوكم ladies. خدام صافي, you can go ahead. So, à vos marques.
3, 2, 1. So the winner is
Oh. Arthur. Arthur Samuel Derrière. فرحهم راهم ربحوا. عطيوك سيرتيفيكا وحده مهزيهم بجوج. ثانك يو. قسيمتها. دوك بيكون 3. جوج بيهم بدات لك القصيده. خذ ديالك راه ديالك. وكا جربتهم بون تيجيو.
Oui, bien sûr, on va refaire la totalité. Il y a des éléments
عجين.
it would be nice to continue working on
Yes.
maybe create your own startup I would encourage you to work more if you believe in something, just work on it and maybe your dream one day will become reality, so just work on it. And also, one thing that I would just want to say is that for pitching, when you're presenting your project, I would really like to work more on pitching because for Juju, they don't know like the hard work that you did. And in your presentation, you show you really like understood what you're doing, and you need to like show them exactly what you did. So show them the objects of your work that's really important. So that's the first thing you start with. What are you trying to solve? What is the problem that you're trying to solve? And also show exactly how you did that. And show them that you understood what you're doing, and then you can find the result. So I would say to work on the fixing part, because your first time do that.
Sorry to interrupt. So sorry. You will be called to deliver the first prize gift. في جبت خونا غادي في جبت عليك بريزونطي. لا تعرفوا سيربريز كلشي كيعرفوا كلشي كيعرفوا تاع سيربريز ديروا
Et les membres du GRI d'avoir honoré
تخيل تربح دوزيام بوزيسيون ما كاينش.
صافي ربحت لنا شكون اللي ربح دابا.
وي شوف وجدوا راسكم غادي نتصور كامل تصور مجموعين. مبروك عليك.
Chers Français, je vous remercie du fond de mon cœur parce que c'est grâce à vous que notre événement a vu le jour et on est déjà à la deuxième édition. Je tiens aussi à remercier les amis du département ThinkAI avec qui j'avais partagé ces 6 derniers mois parce que ça a pris beaucoup de temps. Et à la fin, les amis ici de l'association Malais Maroc avec qui je partage cette passion de mettre en place des initiatives qui on espère, Inch'Allah, vont avoir un impact positif sur le Maroc et en particulier sur la jeunesse marocaine. Et en tant que mentor, j'étais impressionnée par le niveau d'élevé des participants. Ça me fait un peu mal au cœur pas mal d'équipes la meilleure version de l'Hackathon. Puis, nous avons des ressources financières, le podium, ça ne me dérange pas. Malheureusement, il y a 3 places. Donc, bon courage à vous tous.
Et donc, وصلنا the most important part. It's not most important, the winner of this whole hackathon. And again, to keep the swiftiness of this whole thing, I'm going to call 2 special people. First of all, Mr. Abdurrahman Mujjar, our president of Hackathon AI, and Mr. Mohammed Amin Abdul Salah. See? The idea is when you're ready, click it, and everyone will see it at the same time. So you can scream the name. This one? Yes, when you're ready.
1, 2, 3.
The winner is
Chelsea! Thank you. اسمح لي يا Thank you. أكبر راسك. فين هو؟ When you're ready. صور هادو حط. خذ هذه كبيرة. شد معهم. هي.
لا ولكن خصني هو اللي تصور الثاني باقي نتصور
تلعب قطر
لا الثاني باقي لي الثالث
تصور جا اخويا تصور خوشي بدات الصحه والراحه الصحه والراحه الصحه والراحه What did I do? What did I do? See? تبغنيش. You can have a talk if you want.
اش ندير بعد نحطها هنا
نضرب بها راسك اللي بغيت. صافي دابا غادي نعطيو غير السيرتيفيكاسيون ديال بارتيسيباسيون and it's over. Donc ça, you can say something. Yes. السيرتيفيكات ديال 35 سميتك سميتك يسري شنو؟ هاك فين هو سميتو؟ علوي شنو؟ علوي محمدي علوي محمدي علوي محمدي محمد علوي محمدي ضرب معايا طلع ياك محمد علوي حمدي محمد علوي حمدي علوي حمدي محمد علوي حمدي
الكنيه دونك هو محمد علوي محمد
لا 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 مش هاكل صافي 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 الساعة أدرسوا الترتيب الصحة والراحة صافي شوف دي واحد القضية واخا تبريزونتي سلايد ديال موراها نقول خونا يقضي أدرية بقى يدير الأدرية هذاك خونا الدري الضعيف ولا غيعاوننا في البريزونطاسيون ديال هذا يتصور معاهم هما بقاو يعيطوا الدراري واحد يجي
نقول لهم دكتور بالبال انا عاونك
يس 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 واش بالك إلا بغا ما بغاش ماشي مشكل شوف غيوقفوا ونعاونوا نعاونوا حتى حنا نوقفوا جوج ميكرو تصنع شي نسيس وبدنا نصور
نصور
واخا ماشي دابا نطرقوا هادو بعدا واخ صافي سير دود كنبركو نسيلو
دابا غندوزو certificates of participation.
يس بات بيفور يتصوروا التصويره التاليه ديالهم ديال ارثر ورجعوا ضربت عليا قالت لي تصور كمل عليك شوف فيها سين كتشدها لي واش كتشدها اصلا
Alors, la première chose,
نوصل واحد الدور كنوصل باقي ساعه فروماج شوف هكذا كنتوا ساكتين ربحتوا ثم تهلوا غيدير شنو؟ غيسلخك شكون فيهم
المهم سي حسامي كنسناو نصلع حتى انا صويتو
ماشي نقصوا شويه صافي باقي كاين اوكي ثانك يو
راح نبارك عليكم كاملين ندوزو لاخر حاجه هي certificates of participation سي يزيد سيكونسي ممكن يزيد يبقى ريبريزونتي ادريا بزنس اند تكنولوجي
خليل شير نيدد هادشي نتايا غتفرق معنا You can start with any name and we'll keep going. Yes.
So, تمشي الوقت ولكن 3 pages هنايا par classement alphabétique كاين 3 pages هنايا كنبداو ب A هنا كنبداو ب A تمايا من وراها
ابشوي هذيك alphabétique لا راه هي هذيك كنشوف alphabétique ديال الكنيه ماشي ديال so it's fine.
Anyways تبان عندها الميكروفون
Okay, fair. Then we'll start smoothly. يسرى أبو المواهب. والله سيسرى أبو المواهب. اسمعني. تختار
C'est ma cousine, donc je peux me permettre là.
شنو؟ مقاطعة. أمين شو واحد سميتو أمين؟ أمين أحيليل أمين ما كاينش أمين. أمزير محمد علي طبعا اش كيجيك أمزير واحد ديري أمزير تخزله صافي نيفر مايند. عبير الغسلان نعم سي اي صوت الصوره مرحبا هكا لا خليها ثانك يو. بشار محمد. بشار محمد. بشار محمد اجي معي يعني. والدينا والديك. بركة أيوب. بركة أيوب. اسمها جيت تصور قاعد يتصور.
شو سميتش كنت عديو عليهم.
تعديش على بروش محمد. بروش محمد. بروش محمد ما كاينش. ابريش عاودي غياجي. شوف اجي صوري شوف
المهم الصافي مروش كيقول هذا ماشي انا.
ماها
الا عاودت لقيتي شي بريجي واحده اخرى.
اجي انت. هو هي غتصور معاه ولا نصور؟ لا السيرتيفيكا ليهم اجي صور.
اوكي اي ثينك اللي كاين شي بروش محمد مرالك ماشي بروش هذا ماشي انا.
مزيان انت خديتيها كنت غير هادشي.
انت وجد المطار.
بالموسى عبد الرزاق. عبد الرزاق على كيف. زير انت شي مهدي. لا هي هو بن عبد القادر مهدي. ابو مهدي. قد تكون ما ربحتيش ولكن ربحتي قلوبنا كامل.
ويلي ما تلاقيت معاك هذاك هو الدولار في البال.
نجوى الأعمال.
ثانك يو عز. بن جعفر شيماء. بن جعفر شيماء. توما مهدي. نعم.
Word of appreciation for man أحمد عافاك.
Yes. By the way, before we finish, واحد very big word of appreciation for two pillars اللي صراحة كاينين في الباك نعمان وبابا. برجولة the guy helped us mentoring all night and all day, pulled an all-nighter. أحمد راه مازال حوايجو الأول راه he's pulling an all-nighter to make this happen. So please thank you so much. والله بحال هاد لي زيفينمون سمح لي بزاف وقفتك هنايا. بحال هاد لي زيفينمون couldn't happen if it wasn't for you guys. So yeah, thank you so much. If you want to say anything to the kids, please to the men, please do so. If not, a word of appreciation is way more than enough for us. سي بن جعفر ماشي بغي
ولكن صراحه كاين ناجحه بالنسبه لي هو انا مازال تنطلق في هذا الاسبوعين القراءه كثير هادشي مثلا كنتلاقى معاهم بزاف مرات في العام وكنت كاملين entretien خدام وصافي كاين بزاف د الحوايج اللي نعرفوا كتقدروا ديروهم وكتجيبوا بزاف د الهوايات تكون عندكم امباكت في العالم لا من غير خدمه داكشي اللي وحده انا طبيعي نكونوا شوفوا انتم اللي بغيتوا تخدموا في الاسبوع ما شاء الله عليكم.
Sincèrement, je n'ai pas de mots spécifiques à dire. Rien que le fait que كنشوف بزاف ديال الوجوه انا مش ناس ما كاينهم ماشي بحكوا
بقى نقول لك اسمح لنا على البروسي ما تبغاش حساب
هو الفكره شحال من ورقه ما كايناش كنبقى ندرها هذيك السؤال هذيك تبقى تعاود
بالبوك الاميمه ما تخيل ما تجي لك
تقريبا لي بارتيسيبون كنكون دي كيداتكم فاهمان تخيل باش تحاولوا هاد الزياره عندكم لهنا وسط يونيفرسيتي وسط ريستونسيون زورونا دونك جو تيان برينسيبالمون لي ريميرسي توس اما لاغاسيون سترونس فيها عليكم كنتمنى اوسي هادشي يكون بدايه وبديهه كيف عبد الرحمن المجرد هو اللي سال بريزيدون ديال كلوب ريستونس تي اي باش يشجعكم باش او سان دو زيكول مون دي زيفينمون اي اوسي يكون هادشي ان شاء الله طريق ليكم باش ديروا بزاف ديال الحوايج وكنظن سي فريمون لا دي شوز انا باش كنشوف تبارك الله كاع الناس اللي موبيليزاو غير على ولاد ليفينمون ديال المسلمين الدارسي والباقي ديال المنطور بلوس لي كونفيرونسي تاعهم نورمالمون عندكم كاع الحظوظ لي ريسورس باش ان شاء الله تنوصلوا مزيان في الكارير ديالكم.
قلت المره اللي انفسنا واش كتبكي بالضحك ولا كتبكي بالضحك. Thank you so much. Now moving back to the weirdest names. بن كبور آية. Thank you. واه. بالعناية يا يونس. شكرا. الله شاق أرضه صبر أرضه. Thank you. ياسين بن طيفور. أنت هو؟ أجي. هي. Thank you. صورتي؟ برقية معاذ. أليبا معاذ أليبا معاذ. أجي. لا. حف بوسطة ما كاينش ما باليش ما كاينش هو انا حفصة بوسلوم حفصة بوسلوم ما عرفتش لا بوصابون ياك انت بعدا الحمد لله اسمح لي بزاف والله ما نعاني راه ثانك يو رياض ما نقولش كنيه رياض بالطول كاينش بوكيتيه حمزه شنو شرف
صيوري ادريسي طارق
هذه صور غفل عليه سرف عليه واش دزنا ولا لا زرولي احمد امين شبير عوض لا درت مقاطعه عليكم ميتو
ياسين
ثانك يو مزياني ايمان مزياني مزياني ايمان اوكي ياسمين كيفاش مشكل شكرا اعطيني زيد ما عندكش اعطيني
عبد الله ولي
اعطيني جوج اليوبي اسماء اسماء ثانك يو. البشيري محمد، لا البرشيشي محمد. هذاك انت. وكاين بروش محمد.
هذاك ما كاينش.
شي سبحان الله سميت سبحان الله.
ياسين صيوان.
ناضي صحراها كاين باقي زيد. هو زينب الحوز. شد جهه كامله.
زعيد مروان.
بس زيد لا كنجي. الفلالي علي. اي الحطه ولا الحطه سهله فهمتي.
مرابط زكريا.
مرابط مز. رضا القط. رضا ما كاينش رضا القط.
محمد وعائشة.